Finally, we look at two very important problems and instances. These two problems were both defined by Erdos rather a long time ago, and he himself considered these two problems among his most important contributions to geometry. And in fact, these two problems have been very influential among many other researchers and in giving direction to this field. The first problem is about maximizing the number of times a certain distance can appear among pairwise distances of a set of endpoints. You know that if you have endpoints in the plane, if you look at the distance between any two points, you can define roughly n squared different distances. We would like to know how many times a certain distance, let's say unit distance, can appear among all these roughly n squared distances. For example, in this picture, we have 3 points. If this edge length is 1, then distance 1 appears 3 times, which is obviously the maximum possible among a set of 3 points. A related problem is called minimizing the number of distinct distances. Over here, we would like to reduce the total number of distinct distances that we can have among a set of endpoints. Again, in this picture, there is only one distance 1, and it appears 3 times. Let's look at the history of these two problems very briefly. So in 46, Erdos actually defined these two problems. And for the unit distances, he could prove the following bound. So he showed that there exists a point set such that that point set defines at least n to the 1 plus some constant times log n unit distances. In other words, the distance 1 appears at least so many times among this point set. There has been no progress upon improving this bound since then. From the other side, he actually could prove that among any set of endpoints, the unit distance can at most appear n to the 3 over 2 times. So now there is no way to repeat a same distance more than this bound. The bound was slightly improved in 73 and further improved in 84, and finally the best known bound to this problem is n to the 4/3. Looking at the name of the authors, you might have a guess how they proved this. Erdos himself conjectured that this lower bound is in fact closer to the truth. So he actually did not believe that you could in fact create a point set such that the unit distance appears so many times, or n to the 4/3 times. But this is the best known for this problem up this point. Now let's look at the other problem, the number of distinct distances. Erdos himself proved these two bounds. First, he constructed a grid, and in fact he constructed the same square root n times square root n grid, and in such a grid he could prove that there are at most n over a square root log n distinct distances. In other words, such a grid can actually reduce the total number of distinct distances to very, very low. From the other side, he could prove that any set of endpoints create at least square root n distinct distances. So there is no way to reduce a number of distinct distances below square root n. So the true answer is somewhere between square root n and n over square root log n. While the first bound has not been improved, there has been many, many improvements on the second bound. Here we'll look at a summary of these improvements. A few years later, Moser could prove the bound, or increase the bound to n over 2 over 3. So he proved that there are at least n over 2 over 3 distinct distances. Again, this bound was improved further on in 84, which is a rather substantial improvement. Furthermore, this is roughly 0.8 divided by log n over here. This log n term was removed the next year. It was slightly increased in 2001, and we had 2 other papers that had still such crazy bounds, such as this one and this one. And finally, a major result came in 2010 by Good and Katz. As you can see, this bound almost matches the Erdos's upper bound of n over square root log n. The difference between them is a very, very small term of a square root log n. Furthermore, the result in 2010 used a very important technique, or actually they introduced a very important technique using polynomial partitioning method. We will look at some basics of this technique in this course as well. However, for this video, we'll cover this bound here and this bound here. So we'll be covering actually quite decent progress that has been made on these two problems. We'll not be able to cover this proof because it's quite complicated, but we will manage to cover some basics of it further in the future. Okay, let's start by looking at the maximizing the number of times a unit distance can appear among a set of endpoints. Consider your set of endpoints, and let's say these blue edges are the unit distances among these set of endpoints. The first observation is that we can reduce the problem to a problem of incidences between points and circles using the following method. From every point, draw a unit circle. It's obvious that the points that are within unit distance of this point will be on that circle. From every point, we can draw one unit circle, so we have n unit circles, and we also have n points. Every time the unit distance appears in the point set, we'll have incidences between points and circles. So we could have u of n instances between n points and n circles. Actually, we have, in fact, 2 times u of n incidences because this unit distance will induce an incidence over here and over here. But the factor of 2 will not matter for us at the end. So now we look at the new problem. We have n points and n unit circles, and we have u of n instances between them. And we'd like to prove a bound on u of n. The proof is very similar to the proof of Semerdi-Trotter theorem. We know that n circles define less than n squared crossings between them. So again, we build a graph. The points are the vertices of the graph, and edges will be defined by the circles. Now if you look at one circle with t incidences, such a circle defines t edges. 1, 2, 3 for this circle that has 3 points on it. So this means we can use the previous argument. However, notice that we have one big difference between this problem and the Semerdi-Trotter problem, and that is over here we can have multiple edges. For example, these two vertices have 2 edges between them. In other words, the graph that we can obtain from this transformation is not going to be a simple graph. This will be a problem because the bound that we want to use, the crossing lemma, can only be applied to simple graphs. Fortunately, in this problem, there is an easy way to fix it. We could observe that the multiplicity of every edge is at most 2. I leave this as an exercise for you, but assuming this is true, then from every multiple edge, we can delete 1/2. We will be reducing the number of edges by a factor of 2. So in other words, if the number of incidences was I, instead of creating I edges, I will be creating I over 2 edges, because I could remove, in the worst case, half of them. And now we plug in the crossing number lemma. We have n squared crossings. We have at most n squared crossings. And from the crossing lemma, we know that the number of crossings is at least e cubed divided by v squared minus v. By plugging those numbers here, we get to this bound. And after simplification, similar to Semerdi-Trotter theorem, we could prove that the number of incidences between these points and circles is n to the 4/3. And as we discussed at the beginning of the problem, this proves that the number of times the unit distance can appear is at most n to the 4/3.